Hi, my name is Guillaume Pirot and I am Research Fellow at the Center for Exploration Targeting at the University of Western Australia. I want to present you a new method called pilot stick perturbations that allows the propagation of data and algorithmic uncertainty. This work is done in collaboration with Mark Lindsay, Lachlan, Miguel de la Varga, and Mark Jessel. 3D modeling is really useful to support decision making, and it is used to quantify predictive uncertainty. To do that, we need to perform ensemble modeling, which means generating an ensemble of stochastic geological realization. And at the same time, it requires a proper propagation of uncertainty. The two main sources of uncertainty are aleatoric, related to data errors, or epistemic, related to the lack of data at spatial locations that were not sampled, for instance, and to the lack of knowledge that can be, in another way said, as a conceptual uncertainty. In addition, we also need to take into account algorithmic uncertainty. We use algorithms to generate models, and depending on the parameter we use, we can end up with very different results. This is a simple illustration from a paper of Lachlan et al. From 1997, where you can see different potential fields that were interpolated given the same input data, but for different parameters. So there is a huge variability. Here, the parameters involved are the range for the interpolation and the kind of spatial trend in the interpolation. So it's a 0 degree trend, or a linear trend, or a quadratic trend. Data perturbation is well taken into account. So it means perturbation of data positions or orientations and these kind of things. But taking into account the lack of data or algorithmic uncertainty is not always done and not always easy to perform. Sometimes parameters are hidden or not accessible for the user. So here I propose to introduce a fictive drill hole called pilot stick to mitigate this effect. And so we will add perturbations to these fictive drill holes, and these perturbations will be consistent with surface geological observations, with formation thickness, and with possible interpreted horizons. This method is inspired by the pilot point method defined by Cert and de Marcilly. In the pilot point method, that is widely used for parameter estimation, parameters are usually estimated only at the pilot point locations and optimized at this location. And the parameters outside the pilot point locations are interpolated by kriging. How does it work, this pilot stick perturbation methods? Let's consider the following stratigraphy with a youngest formation in grids above a purple one, which sits on a brown one, on top of the oldest one, which is the red one. Here, the dots denote basal content of the formation. The idea is to simulate the thickness of this formation successfully and successively, and to stack them together. So we start with the youngest formation, and basically we randomly draw thickness from the experimental cumulative density function of this formation. Then if it is at the top of close to the surface, we can apply some erosion, and then for the following formation that is below, a bit older, then we randomly draw again thickness from the experimental CDF, and so on. Then we have some conditioning data at these fictive drill hole locations that we add as geological data to our geological modeling engine. With this method, we can also use some estimates of contact interface if we do not have information of basal contacts at the surface. And we can also take erosion into account between grouped formation. I propose to work on a synthetic case. This is inspired by a Precambrian basin setting. So we consider the following stratigraphy here. And we have partial surface geological observations that consist of positions of contacts between lithologies and bedding orientations. To start, simply we assume a conformable stratigraphy, and we rely on estimations of apparent thickness and on sequential Gaussian simulations of orientations and on sequential Gaussian simulations of unit thicknesses to randomly draw the thickness and conditions of pilot sticks that are denoted here in pink and that are on a regular grid 5 by 5 over this domain. We consider 3 geological modeling engines. The first one is a prototype that relies exclusively on the stacking of simulated thicknesses obtained by these pilot stick perturbation methods. The second one is a loop structural geological modeling engine, and the third one is a 3D geomodeler. For these 3 geological modeling engine, we consider 2 perturbation modes. One considers only data perturbations, so we perturb the locations or the orientation of initial data. And the other modes consider pilot stick and data perturbations. Because the prototype model can only deal with pilot stick and data perturbations, we end up with 5 scenarios for which each of them we generate 20 realizations. To measure the geological uncertainty, we use the entropy, and we compute entropy given the probability distribution of the lithofacies in the ensemble of generated geological realizations. These are the results in terms of entropy and geological uncertainty. So in red, you have values of high entropy, and in blue, values of low entropy. So low uncertainty for low entropy and high uncertainty for high entropy. On top, we have results when we only use data perturbations, and at the bottom, when we use both pilot stick and data perturbations. We can see that pilot stick perturbations increase strongly geological uncertainty. But what we can see also is that geological uncertainty varies a lot between each modeling engine. If we look at the total entropy over the volume, we see that we have maximum values for loop structural realizations in any situation. And if we compute the ratio of total entropy, which is total entropy for a given scenario divided by the maximum total entropy that can be obtained. So we have a ratio of 1 in this situation. So for loop structural realizations using pilot stick and data perturbations, here we have 2/3 of this level of entropy, here 1/3. So what did we learn? Pilot stick perturbations increase the geological uncertainty, mitigate the smoothing induced by implicit modeling engines, and account for some of the epistemic uncertainty. Also, spatial geological uncertainty depends on the modeling engine. And some limitations of this work are that we assumed a very simple geology with a conformable stratigraphy. So in further work, we look at more complex features and test also other uncertainty indicators. And one take-home message is that given a conceptual model, uncertainty propagation cannot be limited to data perturbation. With this, I would like to thank our sponsors and partners, and thank you for watching this video.